Welcome to the lecture of Flexible AC Transmission System. We shall continue today with the second type of the static or compensator, that is mechanically switched capacitor type of SVC, and Thyristor Switched Capacitor, that is TCR type of SVC. Now we will see the mechanically switched capacitor type of SVC. Now first of all, we will discuss about the MSC-TCR type of SVC. MSC stands for the mechanically switched capacitor and TCR is the thyristor control reactor, and the combination of both will give you the shunt compensation, that is static var compensation. In this connection, mostly we require a step down transformer to match the rating of the TCR. So here are two configurations. In one, the step down transformer is connected at the common bus bar, or where in second we can connect the step down transformer in series with the TCR. So we have a TCR, and apart from that we have a mechanically switched constant capacitors, and we may have a small value of the inductor in series with the capacitor to prevent the inrush current. And this is a harmonic filter because TCR will generate some amount of harmonics, and that is suppressed by this harmonic filter. So this kind of combination is called the MSC-TCR type of SVC. Here, instead of fixed capacitor, we are using the mechanically switched capacitors. This is the advantage of it because you can connect and disconnect as per our requirement instead of connecting permanently to the line, and it is normally require less amount of switching because you know that there is a constant VAR requirement, let us say around 6 MVA, so you keep it around 6 MVA. If at a moment the requirement is 5.7 MVAR, then you know that TCR will have a capacity to inject minus 1 MVAR, so it will inject minus 0.3 MVAR. So this is the concept of this MSC-TCR. So this capacitor you would not be switching very frequently, and it is only for the maintenance or isolation purpose. It is same like the fixed capacitor type of TCR with more capacitors which can switch stepwise. So here two capacitors are shown. The number of capacitors are connected in parallel and they are switched as per our requirements. A small inductance is connected in series with the capacitor, which is not shown here, and tuned for the selected harmonics. Apart from there should be a harmonic suppression filter. In this also a high pass filter used for the mitigation of the harmonics. Now the purpose of mechanically switched capacitor is to generate a step reactive power. So the reactive power capability will change because you are increasing the admittance of the line. The more capacitive current will be injected and more MVR will be injected into the line stepwise. TCR performs as a controlled reactive power absorption when there is an excess power generation by the capacitor. Suppose line requires compensation of 5.7 MVR and every mechanical switch has a capacity of 1 MVR, so it will go for the 6 capacitors units so that it will generate the 6 MVAR, and 0.3 MVAR will be absorbed by the TCR so that we can get the resultant 5.7 MVAR. In MSC-TCR type of SVC, the rating of TCR is almost equal to the single mechanically switched capacitor rating. Number of capacitors units are more, but the number of TCR unit is only one. As per our requirement of the reactive power generation, the number of switch is on. for the less reactive power generation, less number of switches may be on. Definitely, if line requires a compensation of the 3.4 MVAR, then you will actually switch off other 2 MVARs and only 4 will be in service, which gives the 4 MVAR, and 0.6 MVAR will be compensated by the TCR. So you will get resultant 3.4 MVAR. So the advantage of this is that there is no complexity in it, and we will switch it on whenever our requirement is high and switch it off when this requirement is low. So we will have a better capacity utilization of capacitor bank as the system requirement. The capacitive current will be injected in quadrature with the current, which improves the power factor. So the advantage is that it is having low cost, then lower loss, and better capacity utilization of the capacitor. During maintenance, all capacitors need not to be switched off. The disadvantages are more because it is putting up in practice before the fact devices. So it has this slow response due to the mechanical switching. The switching closes around 2 cycles, so for this reason we require to insert the capacitor very slowly, and that leads to the subharmonic oscillation, and it will open in the 8th cycle, so that we need to check whether it requires time to gradually dissipate the power and open slowly. So it is not used for the fast and large dynamic reactive power variation. In VAR, demand would repeatedly change above and below this level, at which the capacitor bank is switched in and out. Then the MSC-TCR type of SVC cannot be used because switching life is limited to 2000 to 5000 times only. So we have to operate this in a very constant manner so that we can use it for the longer duration. Another disadvantage is that the tapped energy in the capacitor bank, which result in the transients. So the capacitor always been a little nasty when actually transient phenomenon occurs. Therefore, each capacitor has to be completely discharged through a better resistor, which makes around 8 minutes to dissipate all the energies before being switched. And we can also use the potential transformer, but generally it will also increase the cost. So we can conclude that because of much slower response and the limitation of them in the execution of the capacitor switching, the output of the MSC-TCR combination would be able to follow a changing reactive current reference quickly. So we had to be fitted with dynamically controlled TCR. It can be used where the rate of change is very slow, or in a single step like change must be taken place at a time when the capacitor is already discharged, and we can go for the next switching stage. The Thyristor Switched Capacitor and SVC is another combination. So in TSC-TCR, you may have smooth variation of capacitor instead of the fixed capacitor as in FC-TCR, or instead of put it on and off by the mechanical switches as in MSC-TCR. Now you may have a TSC-TCR in combination, so then you are also have a Thyristor switch to manipulate or turn on and off the capacitor, as well as you have a TCR. The Thyristor Switched Capacitor and Thyristor Controlled Reactor type of compensator was developed for the dynamic compensation with the minimized standby losses and providing increased operating flexibility, because you can also frequently turn it on and off. It does not having the disadvantages of low switching frequency. that is already there. Apart from that, you have a TSC so that it can be turn on and turn off very frequently. A basic single phase TSC-TCR type of SVC consists of n TSC branches. So here are number of branches of TSC and number of branches of TCR is only one. So this is one TSC, this is another TSC, this is third TSC, so up to number n, and this is one TCR. So accordingly TSC will increase the VAR compensation, and whatever the negative portion it will be compensated by the TCR. So let us say you are having the rating of 1 MVA of each TSC. Again with the same example, here you require this 7.6 MVAR. So what will we do? We will actually switch on 8 of such units, so that we will get the 8 MVAR here, and the excess 0.4 MVAR will be absorbed by this one TCR. That is the principle of operation of this combination. So here we have controlled the VAR generation in both TSC and TCR. Thus, the number of branches n, which is determined by the practical consideration that include operating voltage level, then maximum VAR output, then the current rating of the thyristor valves, etc. etc. The inductive range also can be expanded to any maximum rating by employing additional TCR or TSRs, that is segmented TCR branches. So you can add one branch of TCR if required. Now we will see the operation. The total capacity output range QC max is divided into the n intervals. So in the first interval, the output of the VAR compensator is controllable in the 0 to QC max divided by n range. So total range is QC max, and it is divided into n number of TCR. So for one TSC we will get the QC max by n range. In this interval, one capacitor bank is switched on by the switch SW1, and simultaneously the current in the TCR is set by the appropriate firing delay angle, so that the sum of the VAR output of the TSC and TCR equals the capacitive output required. So it will compensate the negative VAR. In second, third and up to the nth interval, the output is controllable simultaneously in the QC max by n to 2 QC max by n, then 2 QC max by n to 3 QC max by n, and n minus 1 QC max by n to QC max by n, by switching in simultaneously the second, third, fourth up to the nth. By using the TCR to absorb the surplus capacitive VARs. So you can have a step change in operation of the compensating VAR. We will see in the waveform. In all intervals, surplus of the reactive power is absorbed by the TCR. That is what I was saying. The maximum surplus capacitive VAR in the total output range can be restricted to that produced by the one capacitor bank. So theoretically, TCR should have a same VAR rating as a TSC, but to ensure that the switching condition at the endpoint of the intervals are not indeterminate, so the VAR rating of the TCR has to be somewhat larger in practice than one TSC in order to provide enough overlap or the hysteresis band between the switching in and switching out the VAR levels. So the VAR rating of the TCR has to be somewhat larger than QC max by n, that is the rating of